Look up on a clear night, away from the wash of city lights, and you will see something that has stopped humans in their tracks for as long as there have been humans to stop. A few thousand points of light scattered across the dark, each one a sun, some far larger than our own, some so distant that the light striking your eye tonight left its source before humans had learned to write. And that is only what your naked eye can catch. Turn a telescope skyward, and the numbers become almost abusive to intuition. Hundreds of billions of stars in our galaxy alone, and hundreds of billions of galaxies beyond that, each one its own island of hundreds of billions of suns. Somewhere in that number, buried in a calculation so large it stops meaning anything to our evolved primate brains, sits a question that has haunted scientists, poets, and late-night stargazers alike. Are we alone? It sounds like a simple question. It is not. To even begin answering it honestly, we have to do something that feels almost like cheating. We have to set aside the science fiction, the flying saucers, the little green men, and go back to the deepest, strangest, most well-tested physics we have, the physics of space, of time, of the universe's birth, and possibly of realities tucked into dimensions we cannot see, and ask what that physics actually permits and what it forbids. Tonight, that is our journey. Not a guest dressed up as science, but real physics, pushed as far as it can honestly go, aimed at the biggest question we know how to ask. Let's start where any honest conversation about the universe has to start. With Einstein, because everything else we will talk about tonight, the Big Bang, the shape of extra dimensions, even the very possibility of ever meeting whatever else might be out there, rests on the revolution he set in motion. Before Einstein, space and time were thought of the way most of us still think of them in daily life, as a fixed stage and a universal clock. Space was the box the universe sat in. Time ticked forward at the same rate for everyone, everywhere, an unchanging metronome running in the background of reality. It's an intuitive picture. It's also, we now know with overwhelming experimental confidence, wrong. Einstein's special relativity, published when he was still a young patent clerk with more curiosity than credentials, showed that space and time are not separate, fixed backdrops, but a single flexible fabric, space-time, and that how fast you move through space changes how fast you move through time. Get in a spaceship and accelerate to a meaningful fraction of the speed of light, and your clock, relative to someone who stayed home, runs slow. Not as an illusion, not as a trick of instruments, but really physically slow, in a way that has been measured directly, with atomic clocks flown on airplanes, with muons raining down from the upper atmosphere, with the GPS satellites orbiting overhead right now, which have to correct for relativistic time dilation or the whole system would drift into uselessness within a day. Time, it turns out, is not a universal river flowing at one rate for everyone. It is personal. It depends on your motion. Then, a decade later, Einstein went further with general relativity, arguably the single most beautiful theory in the history of science. He asked what gravity actually is, and the answer he arrived at overturned Newton's picture entirely. Gravity is not a force reaching invisibly across empty space, tugging planets toward the sun. Gravity is geometry. Mass and energy bend the fabric of space-time itself, the way a bowling ball dropped onto a stretched rubber sheet creates a dip, and other objects moving nearby simply follow the curves in that fabric. The Earth orbits the sun not because it's being pulled by some ghostly hand, but because the sun's mass has warped the space-time around it. And the Earth is simply following the straightest possible path through a curved landscape. This isn't poetry. It's been tested to extraordinary precision in the bending of starlight around the sun during eclipses, in the slow precession of Mercury's orbit that had puzzled astronomers for decades, in the direct detection of gravitational waves, ripples in space-time itself spreading outward from colliding black holes a billion light-years away, and finally washing over detectors here on Earth a century after Einstein predicted they should exist. Why does any of this matter for the question of aliens? Because relativity sets the rules of the playing field for any conversation about contact with another civilization, and those rules are brutal. Einstein's equations show that nothing, no signal, no spacecraft, no information of any kind, can travel through space faster than light. Light itself takes over 4 years just to reach us from Proxima Centauri, the nearest star beyond our own sun. It takes about 100,000 years to cross our galaxy alone, and our galaxy is one undistinguished speck among hundreds of billions. If there is a civilization circling a star on the far side of the Milky Way, and they beamed a signal toward us the moment their own civilization first discovered radio waves, that signal is still, right now, only partway through its unimaginably long crossing. Space is not just big. Under the physics we actually have, confirmed again and again in the laboratory and an astronomical observation, space is close to insurmountable. This is the first hard truth that any serious conversation about intelligent life elsewhere in the universe has to reckon with. The universe may be teeming with minds, and the geometry Einstein uncovered may keep almost all of them forever out of reach of one another, not because nature is being cruel, but because that is simply the shape of the arena we live in. And yet, space-time being flexible is exactly what keeps the conversation from ending there. If gravity is geometry, if space itself can stretch and warp, then the question naturally arises, could space-time be bent or folded in ways that shortcut the vast distances between stars? This is where wormholes enter the conversation, and it's worth being precise about them because science fiction has run away with the idea more than the physics currently supports. General relativity's equations do allow, mathematically, for tunnels connecting distant regions of space-time, first noticed by Einstein himself working with Nathan Rosen. But the equations also demand something to hold such a tunnel open against its own tendency to collapse, something physicists call exotic matter, matter with negative energy density, and while quantum theory permits tiny, fleeting patches of negative energy in very specific circumstances, nothing we know of comes close to producing or sustaining the quantities a traversable wormhole would need. So wormholes remain, for now, a mathematically legal but physically unrealized possibility. A reminder that the equations of general relativity are more permissive than the universe we've actually observed, and that the gap between what the mathematics allows and what nature actually builds is one of the great open puzzles at the frontier of physics. To understand why the universe is arranged the way it is, why there are stars and galaxies and planets scattered through these vast reaches of space at all, we have to go back, not just centuries, but almost 14 billion years to the very beginning. The Big Bang is one of the most misunderstood ideas in popular science, so let's be careful with it. It was not an explosion happening at some location within a pre-existing empty space, the way a bomb detonates in a room. It was the beginning of space itself. Every point in the universe today, if you ran the clock backward, converges toward a single, unimaginably hot, unimaginably dense state, roughly 13. 8 billion years ago, from which space itself began expanding and has been expanding ever since. We know this not from speculation, but from multiple independent lines of hard evidence that all agree with each other. We see distant galaxies systematically redshifted, their light stretched exactly as you'd expect if space between us and them is expanding. We detect the cosmic microwave background, a faint bath of radiation filling the entire sky, the cooled down afterglow of the hot early universe, its patterns matching predictions to a precision of 1 part in 100,000. We measure the relative abundance of hydrogen and helium and lithium across the cosmos, and it matches with remarkable accuracy what the physics of the first few minutes after the Big Bang predicts should have been forged. 3 independent lines of evidence converging on the same story. This is not a theory hanging by a thread. It's one of the best supported ideas in all of science. What the Big Bang gives us for tonight's purposes is scale, both in space and in time, in the roughly 13. 8 billion years since that beginning, matter that was once smoothly spread through the infant universe has clumped under gravity's patient pull into galaxies, into stars, into planets. Our own sun is a relatively young star, a third-generation star even, built from the recycled remains of earlier stars that lived, fused heavier elements in their cores, and died in supernovae that seeded space with carbon, oxygen, nitrogen, iron, the very atoms that make up you, me, and every living thing on Earth. We are, in the most literal sense the Big Bang and stellar physics can offer, made of stardust, forged in the deaths of stars that existed and expired long before our sun ever ignited. And crucially, that process has been running for billions of years across hundreds of billions of galaxies, each with hundreds of billions of stars, a huge fraction of which we now know from missions like Kepler and TESS host planets of their own, We've directly confirmed more than 5,000 exoplanets, and statistical extrapolation from what we've found suggests our galaxy alone may host tens of billions of roughly Earth-sized worlds orbiting in the temperate zone where liquid water could exist. That number, run across the cosmos as a whole, becomes almost incomprehensibly large. The Big Bang doesn't just tell us how the universe began, it hands us the raw material and the staggering scale on which the question of life elsewhere has to be considered. This is where it becomes tempting to reach for a tidy conclusion. Surely, with that many planets, life and even intelligence must be common. But physics demands more honesty than that. And this is where the Fermi paradox enters the story. The physicist Enrico Fermi, sitting at lunch with colleagues in 1950, is said to have asked a deceptively simple question given the sheer number of stars, the age of the galaxy, and enough time for even slow interstellar travel to spread a civilization from star to star over a few million years. A blink of an eye on cosmic timescales, where is everybody? The silence we observe, the total absence so far of any confirmed signal, probe, or artifact from another civilization, is itself a piece of data, and it's a puzzling one. There are many proposed resolutions, and honesty requires admitting we don't know which, if any, is correct. Perhaps life itself is common, but the leap to complex, intelligent, technological life is extraordinarily rare. A bottleneck hidden somewhere in the chain from simple chemistry to self-replicating cells to complex organisms to intelligence to technology capable of sending signals across the stars. Perhaps civilizations do arise regularly, but tend to be short-lived, undone by the very technological power that lets them broadcast their presence. A sobering thought given our own species' present relationship with nuclear weapons, climate systems, and artificial intelligence. Or perhaps, and this is where relativity comes back into the story, civilizations are common but simply too far apart, too separated by the light speed limit and the sheer geometry of space and time, ever to notice one another within the brief window that either exists to listen. There's a famous informal tool for organizing our ignorance about all of this called the Drake equation, put together by the astronomer Frank Drake in 1961, not as a way to compute a definite answer, but as a way to structure the conversation, to break an overwhelming question into smaller pieces we could, at least in principle, work toward measuring. It multiplies together things like the rate at which stars form in our galaxy, the fraction of those stars with planets, the fraction of those planets that could support life, the fraction on which life actually arises, the fraction of that life which becomes intelligent, the fraction of intelligent life that develops technology capable of broadcasting its presence into space, and finally, the length of time such a civilization continues broadcasting before, for whatever reason, it stops. What's striking, looking back at that list 6 decades later, is how much of it has moved from pure guesswork into genuine, measured science. We now know, thanks to missions like Kepler and Gaia, roughly how many stars our galaxy contains and roughly what fraction of them host planets, and that number turns out to be close to all of them. What we still don't know, and what remains almost entirely a matter of speculation rather than measurement, are the later terms in the equation, the ones concerning the jump from simple chemistry to life, and from life to intelligence, and from intelligence to a civilization capable of, and interested in, reaching across interstellar space. Those middle terms could each independently be common or vanishingly rare, and until we have more than a single data point, our own solar system, to work from, the equation, however useful as a way of framing the problem, can't give us a reliable number, only a way of seeing exactly where our ignorance is concentrated. That's part of why so much of the actual observational effort today has shifted towards something more tractable than detecting an intentional signal, looking for biosignatures, the chemical fingerprints life leaves on a planet's atmosphere, whether or not that life ever develops technology at all. Telescopes like the James Webb Space Telescope can now split apart the faint light passing through or reflecting off the atmosphere of a planet orbiting a distant star and read out from the pattern of absorbed wavelengths which molecules are present. Oxygen is a particularly interesting target because it's a highly reactive gas that tends to disappear quickly through chemical reactions unless something, generally photosynthetic life, is continuously replenishing it. Combinations like oxygen alongside methane are even more suggestive because the two react with each other and shouldn't coexist in stable, persistent quantities unless something is actively producing both at once. None of this would prove intelligence, of course. A planet thick with microbial life, The way Earth was for roughly 3 billion of its 4.5 billion years of history would show biosignatures without ever hosting anything capable of building a radio telescope. But it would answer, at least partially, the very first and most basic term buried inside the Drake equation and inside tonight's whole question. Not whether intelligence is common, but whether biology itself, the spark that could eventually lead to intelligence, is a common outcome of physics and chemistry running their course on a temperate rocky world, or whether Earth's living, breathing biosphere is some kind of staggering cosmic rarity. Now let's push the physics one step further into territory that is more speculative, more mathematically adventurous, and further from direct experimental confirmation, string theory. It's important to be upfront about where string theory currently sits. It is a serious, mathematically rich framework pursued by many of the finest minds in physics, aimed at solving one of the deepest problems we have, which is that general relativity, our theory of gravity and the large-scale universe, and quantum mechanics, our theory of the very small, don't fit together. Apply the equations of general relativity at the scale of a subatomic particle, or the equations of quantum mechanics to the crushing gravity inside a black hole, and both theories break down, spitting out nonsense like infinite values where there should be sensible numbers. String theory proposes that the fundamental constituents of reality are not point particles, as the standard model of particle physics assumes, but tiny, vibrating strands of energy, so small that no experiment we can currently build could resolve their structure directly. Different vibrational patterns of these strings, the theory suggests, correspond to different particles. An electron is one note, a quark another, and remarkably, one particular vibrational pattern has exactly the properties we'd expect of the graviton. The particle that would carry the force of gravity, meaning gravity falls naturally out of the mathematics rather than needing to be bolted on by hand. That's part of why so many physicists find the theory compelling despite its lack, so far, of direct experimental confirmation. But here's the detail that matters most for tonight's question. For the mathematics of string theory to be internally consistent, to avoid contradictions and negative probabilities, the equations require more than the 3 dimensions of space and 1 of time we experience. Depending on the specific formulation, string theory calls for 10, 11, or in some versions, 26 dimensions total. Since we only ever perceive 3 spatial dimensions plus time, the theory proposes that the extra spatial dimensions are curled up, compactified into shapes so small, far smaller than an atom, smaller even than anything we can currently probe, that we simply never notice them in ordinary life. In much the same way a garden hose looks like a one-dimensional line from far away, but is actually a 2-dimensional surface curled into a tube. Once you get close enough to see it properly, the precise geometry of those curled up extra dimensions, mathematicians and physicists have shown, determines the masses of particles, the strengths of forces, the entire roster of physical constants that make our universe look the way it does. And here is the genuinely strange part. The mathematics doesn't point to one single way to curl up those extra dimensions. It points to an almost incomprehensibly vast number of possible configurations, sometimes estimated at something on the order of 10 to the 500th power or more. Each configuration would produce a universe with different physical laws, different particle masses, different values for the fundamental constants. It's worth pausing on just how strange this landscape idea is, because it's easy to let a number like 10 to the 500th power slide past without really absorbing it. That's not a large number in the ordinary sense. It's a number so large that if every particle in the observable universe, something on the order of 10 to the 80th of them, were itself an entire separate universe, and each of those contained another 10 to the 80th particles, you still wouldn't approach it. Each one of those configurations, mathematically speaking, is a candidate description of a universe, complete with its own version of the electron's mass, its own strength of the electromagnetic force, its own version of the constant that governs how tightly protons and neutrons bind together inside atomic nuclei. Change that binding constant by even a percent or two in either direction, and stars stop being able to forge carbon, or hydrogen fails to fuse at all, and you get a universe with no stable chemistry, none complex enough for anything a physicist would call life. Our own universe sits, as far as we can tell, in a strangely narrow range of settings that permit stars, chemistry, and stability all at once. A fact physicists call the fine-tuning problem, and part of the appeal of the landscape and multiverse ideas is that they offer a possible explanation. If there really are close to infinitely many regions of reality, each with different settings, then naturally, life and observers capable of asking these very questions would only ever arise in the rare bubbles where the settings happen to permit it. In much the same way you'd only find fish in the parts of the ocean that actually contain water. That reasoning, sometimes called the anthropic principle, remains controversial among physicists, precisely because it can feel like an explanation flexible enough to accommodate anything and therefore risks predicting nothing new. And that tension between explanatory power and testability is exactly the kind of honest disagreement that makes this frontier of physics so alive right now, rather than settled. This has led a significant number of physicists, including some of the theory's own architects, to a picture called the multiverse, or more precisely, in this context, the string landscape. The idea that if these extra dimensions can be curled up in vastly many ways, and if some process, perhaps rooted in cosmic inflation, the extraordinarily rapid expansion thought to have happened in the universe's first fraction of a second generates many separate expanding regions of space, each locked into its own configuration of curled up dimensions, then what we call the universe might actually be one bubble among an enormous, perhaps infinite ensemble, each with its own version of physics. I want to be careful and honest here, because this is exactly the kind of idea that gets overstated in popular science content, and precision matters. The multiverse, in this string theoretic sense, is not yet an experimentally confirmed feature of nature. It is a consequence some serious physicists derive from taking the mathematics of string theory and inflationary cosmology at face value. And it remains for now extraordinarily difficult to test directly, which is precisely why some other physicists remain skeptical of how much weight it should be given. But if it is correct, even in rough outline, it reframes the entire question of intelligent aliens in a way that goes far beyond simply asking whether there's life on some other planet in our own observable universe. It raises the possibility that entire other universes with entirely different laws of chemistry and physics, some perhaps far more hospitable to complexity in life than our own, and others perhaps far less so, might exist forever cut off from us, not by mere distance the way other galaxies are, but by something more fundamental, a difference in the very rules by which reality operates. Let's bring all this together now, because that's really the heart of tonight's question. Suppose for a moment that intelligent life does exist elsewhere, whether across our own galaxy, in some distant galaxy billions of light years away, or even if the more speculative multiverse picture has any truth to it, in some other bubble of reality with its own physical constants entirely. What would physics actually allow us to say about the nature of such intelligence, and about our prospects of ever knowing it's there? The first unavoidable constraint is the one Einstein gave us: the speed of light. Any civilization we might detect is not just far away in space, but far away in time as well, because we would be seeing them or hearing them as they were however many thousands or millions of years ago their signal left home, not as they are now. Communication, in any meaningful back and forth sense, becomes almost a contradiction in terms across galactic distances. A conversation where each reply takes centuries or millennia to arrive is barely a conversation at all, more like two civilizations leaving messages in bottles for descendants they will never meet. The second constraint comes from the Big Bang's timeline. The universe needed billions of years to forge through generations of dying stars. The heavier elements that seem to be prerequisites for complex chemistry and life as we understand it, which means truly ancient technological civilizations, if they exist, have had a staggering head start on us, potentially millions or billions of years, which is both a humbling thought and, some argue, part of why the silence of the Fermi paradox is so puzzling. A civilization even a few 100,000 years more advanced than ours could plausibly have spread signals or itself across the galaxy by now, and yet we see nothing. And the third consideration, the one string theory contributes, is perhaps the most mind-expanding of all. It suggests that even the concept of what life or intelligence could look like might not be limited to variations on the carbon and water chemistry we know from Earth. If the string landscape picture holds even a grain of truth, there could be regions of reality, whether other bubbles of an inflating multiverse, or more conservatively, simply distant environments in our own universe, where the fundamental constants of physics differ enough that entirely different chemistries, entirely different forms of organized complexity could arise following rules we haven't even imagined, because they don't operate under the specific fine-tuning of forces and particle masses that our corner of reality happens to have. This is speculative, and I want to say that plainly rather than let the wonder of the idea overstate its scientific standing. But it captures something important about how physics reframes the search for aliens. It's not really a biology question or a question about probability alone. It's a question that, at its deepest level, is about the geometry of space-time, the timeline set by the Big Bang, and possibly the architecture of dimensions curled up smaller than we can currently probe. So, where does that leave us practically? It leaves us in a strange and, I think, genuinely beautiful position. The physics we have gives us every reason to think the raw ingredients for life, planets, water, the chemical elements forged in stars, are common, staggeringly common, scattered across hundreds of billions of galaxies. And that same physics gives us every reason to think that even if intelligent life is out there, relativity's speed limit and the sheer geometry of cosmic distances may keep most of it forever beyond our reach. Unaware of us as we are of them, two ships passing not just in the night, but across gulfs of space and time, so vast that passing barely applies. It's worth sitting with that for a moment, because it reframes what the search for extraterrestrial intelligence really is. Projects like the search for extraterrestrial intelligence, scanning the sky for anomalous radio signals, or missions searching exoplanet atmospheres for biosignature gases like oxygen or methane in combinations that shouldn't persist without something alive producing them, aren't really searching for a certainty. They're searching, honestly, for a whisper across an ocean so large that even a positive result would likely represent contact not with a civilization as it is today, but as it was when the light or the radio waves first left home, possibly long before humans existed at all. And maybe that's the right note to end on, not with an answer, because science, done honestly, rarely hands us the clean answers we want on the biggest questions, but with the shape of the question itself, sharpened by everything we've walked through tonight. Einstein taught us that space and time are not a fixed stage, but a flexible personal fabric, one that both connects every point in the universe through mathematics and, through that same mathematics, keeps almost everything in it out of reach of everything else. The Big Bang taught us where the raw material for planets, chemistry, and life ultimately came from, and just how much time and how much space that process has had to work with, 13.8 billion years across a universe that may contain more planets than there are grains of sand on every beach on Earth. And string theory, more speculative but no less awe-inducing, opens the possibility that reality itself may be built from more dimensions than we can perceive, arranged in more ways than we can count, some of which, if the theory is on the right track, might harbor forms of organized complexity we don't yet have the imagination or the vocabulary to describe. Whether or not there is someone else out there right now, looking up at their own night sky, wondering the very same thing about us, is a question physics cannot yet answer with certainty. But what physics can tell us, with real confidence, is that the universe is vast enough, old enough, and strange enough that the honest answer isn't no. It's simply not yet known, and perhaps, given everything we've just discussed about the limits imposed by light, by time, and by the sheer scale of it all, not knowable in any of our lifetimes. And there is something quietly humbling and quietly wonderful in realizing that the search for another mind out there in the dark is really, when you trace it all the way down, a search conducted using the deepest tools we have for understanding space, time, and the origin of everything, which means that even if we never find them, the questions this search forces us to ask about our own universe make it a journey worth taking regardless of the destination.